Okay, so this is going to be about precipitate reactions. Precipitate not in the sense of rain or snow, but in chemistry. A precipitate is an insoluble product. So remember, soluble means able to be dissolved in water. So insoluble means it does not dissolve. So if we look at this example, in the first picture, we have two clear colorless liquids. And then so what it's actually showing here, if we look at the atomic level, is we have Pb, which is lead 2 plus, so we have lead 2, and then NO3, remember, is nitrate, so we have NO3. And then over here we have the potassium ion as well as the iodide ion. When the two are mixed, there's an obvious reaction there because now we have this yellow substance that was produced, which we didn't have before. Okay, so this yellow substance is called a precipitate. And so if we look over here, we still have some ions, but now we have a much more structured solid, showing that something was insoluble. Okay, if we look at the different atoms and the color coordination that they were given, we can see that we still have nitrate ions in liquid form, and this would be the potassium ions still in liquid form. So this is that same example written out in a chemical equation. So we have potassium iodide, aqueous, meaning it's dissolved in water or it's in solution. Then of course lead 2 nitrate, also aqueous, which is what we began with. And if you remember, these are both compounds, so this is actually going to be a double displacement reaction. So we have potassium nitrate aqueous and then lead 2 iodide solid. And that's what was shown here. So now the question is, how are we going to determine whether something would be aqueous or solid in solution? And so what's actually been done is lots of scientists did lots and lots of studies in combining different chemicals and came up with the list of solubility rules. Do not copy this down. You should get a printed copy. Okay, so to avoid confusion, if it's soluble, that means it'll be aqueous. Okay, so soluble compounds all contain these things, but here's common exceptions. So if it's one of these, it's soluble unless it's got these. Okay, the bottom half, these are insoluble compounds. So these are not going to be aqueous unless they are with these. Okay, so it's kind of reverse. So NH4, ammonium, if it contains ammonium, it is going to be soluble, and for exceptions, there are none. So if there's a compound that has ammonium, it will be soluble. Same with nitrate, cyanide, and all of these others. When we get down here, if we have like bromine ion or chlorine ion, they're going to be soluble unless there was silver, lead, mercury, blah, 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 blah. Now down at the bottom, these are going to be insoluble unless they're with an alkali metal or of course ammonium. As another example, we have silver sulfate, which is aqueous. If we look back over at our chart, so I'm going to flip screens for a second. Sulfate right here is soluble. These are the exceptions. Silver is not one of those exceptions, so it is soluble, which is why we put aqueous. Sodium nitrate, I'm going to tell you right now, whenever there's an alkali metal, it will be aqueous. Whenever there's nitrate, it will be aqueous. Okay, so 2 minus for the sulfate. Remember, when it's aqueous, when they're ionic compounds, they are going to dissociate. So we have our -2 for sulfate. And then I have my +1 for silver. Notice that I have double the amount for silver because there's 2 silvers for every 1 sulfate ion. For sodium, we have +1, nitrate -1. It's a 1-to-1 ratio, which is why I have 1 plus for every 1 minus. This would also be a double displacement reaction. So the products would be silver nitrate and sodium sulfate. So remember, anytime there's a nitrate, it's going to be aqueous. Anytime there's an alkali metal, it's going to be aqueous. So if we have two aqueous products, sorry, and to balance the equation, two silver nitrates, two sodium nitrates. But whenever we have aqueous products, we just have a bunch of ions mixed together. So in actuality, there is no reaction that's occurring. There is no product being formed. We're just mixing the ions together. So if both products are soluble, we consider this no reaction. Okay. Now we're going to look at what are called ionic equations and spectator ions. So of course the chemical equations show the chemical formulas without indicating ionic characters, so not including the charges, just straight up what's reacting, what's being produced. The complete ionic equation shows the strong electrolytes as ions, because that's what happens when they're in aqueous solutions. They're actually as ions. So potassium iodide becomes the potassium ion and the iodide anion. Notice, for the balanced equation there was two of them, we do still have a balanced complete ionic reaction. Lead, this is actually lead 2, hence the 2 right here. So that's why we have lead 2 plus. But in the same breath, this 2 indicates we have 2 nitrates. And then we have lead iodide, which is solid, and then potassium nitrate, which is also aqueous. So because this is solid, this is not aqueous. It does not dissociate. This remains solid. But since this is aqueous, we're going to go ahead and dissociate it into its respective ions. If you notice, on the reactant side and on the product side, some of the ions are repeated, and they're repeated as ions. That's the key here. These are called spectator ions. They don't actually play a role in the reaction. So the net ionic equation is only the ions and compounds directly involved in the reaction shown, which would be 2 of the iodide ions, the lead ions, and it produces the lead 2 iodide solid. Again, since it is solid, it does not dissociate into the ions. So if we look at another example, which ions, if any, are spectator ions in this reaction? So we have sodium chloride, which is aqueous, silver nitrate, also aqueous, and it's going to produce silver chloride, a solid, and sodium nitrate, which is aqueous. Okay, so the first thing I want to do is I want to break up the strong electrolytes into their respective ions, which are when they're aqueous. So sodium and chlorine, silver nitrate, and then since this is solid, it does not get broken up into ions. And then we have sodium and nitrate. And keep in mind they're ions, so we are showing all the charges and showing the states of matter, aqueous or solid. So if we look at this, this would be the net ionic equation. Personally, this kind of bugs me because cation should always go first, but I copied it directly from the above reaction, showing that the chloride anion was first. It doesn't really matter, it's just my preference. However, when you are writing the chemical formula, keep in mind that cation always goes first. So this would be our net ionic equation, but it doesn't really answer the question that's being asked. It's asking what are the spectator ions in this reaction. So what we need to look at is, are there any ions that are repeated on the reactant side and on the product side? And so we have sodium on both sides, and we have the nitrate ions on both sides. So our spectator ions are actually the sodium ion and the nitrate anion.